Thank you. Good morning, everybody. How are you doing? Good. I couldn't quite hear that. What was that? How are you doing? Good. Excellent. I'm doing well, too. So as your principal said, I'm Scott.
I'm Conan.
I'm Lauren. I'm Taylor.
I'm David.
And I'm Katrina.
And we're the University of Illinois Physics Van. So we're a traveling science show. We're all students at the University of Illinois, and we pack up all of our equipment into our van, and we travel around to schools just like yours to try and teach you guys a little bit about science. So to start off, I have a question for you guys. Who knows, what is science? Who has a good idea? Yeah, what do you think? The study of how things work. Right, that's a really good answer. How about a couple more answers about what science is? Yeah, what do you think? What was that? Could you repeat it? A chemical reaction, exactly. That's part of science. We study what happens when we mix chemicals and see what happens. Okay, how about one last answer? These are all really good answers. In the green. Exactly, that's a very good answer. The study of how everything in our universe works. So in science, we like to study all kinds of different things and figure out how the world works. So a scientist is a person who studies science. Now, does anybody know, what does a scientist look like? Yeah, what do you think in the red striped shirt? Yeah, they have a white lab coat. That's a really good answer. How about a few more answers? Yeah, what do you think? Yeah, they have glasses. They have safety glasses, right? That's right. How about one more answer? What do you think? Gloves, right, exactly. You know, and they have the gloves and they have their flasks and they're mixing chemicals all the time, right? Okay, maybe they have crazy hair too. Yeah, okay. So, with that picture in mind, would you guys believe me if I told you that I was a scientist? Yes? Okay. What if I told you all of my friends in the physics van were also scientists? Would you believe me? Yes? Okay. Now, what if I told you that each and every one of you was also a scientist? Would you believe me then? Yes, no's. I'm getting some yeses and no's. Okay. Well, a long time ago, there was a scientist. His name was Albert Einstein. You might have heard of him. And he said that anybody who wonders about why something happens is a scientist. So if you've ever wondered, why is the sky blue? Or where does the sun go at night? Or why is my little brother or sister so darned annoying? Then you're a scientist too. Okay. So as scientists, we like to study stuff and learn about how stuff works. So can everybody point to some stuff for me? Where's some stuff? Yeah, exactly. Everywhere. So if you pointed anywhere, you pointed at stuff because stuff is all around us. So is this pencil stuff? Yes? Okay. Now if I break it in half, is it still stuff? Okay. Now what if I break it in half again? Is it still stuff? Okay. Now what if I keep breaking it in half until all that I'm left with is the tiniest, ittiest, littlest bit of pencil that we could ever have? Is that littlest bit still stuff? Okay. Now there's a very specific word for the smallest bit of stuff we can have. Does anybody know what this word is? Yeah. A molecule. That's a really good answer. There's actually, you can get a little bit smaller than a molecule. Does anybody know what this word is? Yeah. An atom, exactly. All stuff is made out of atoms. And so these atoms that make up all the stuff around us, they can arrange themselves in a few different ways. And we call these the different states of matter. So does anybody know one of the states of matter that atoms can arrange themselves in? Yeah, in the red. Yep. A solid, exactly. That's one of them. There are two more. Who knows one of them? Yeah. A gas. And there's one more. Who knows it? In the tie-dye. A liquid, exactly. Solids, liquids, and gases. So the atoms and stuff arrange themselves into these different states of matter. And to help demonstrate this to you guys, I'm going to need a few volunteers from the audience to be atoms for me. All right. How about one? Can you come up here? Two in the red. You come up here. Three, and one more. How about you? Come on up. All right, and I'm going to get some of my friends from the physics van here. Oh, no, sorry, I said this to you. Okay, come on up here. And you guys are going to stand in between my physics van friends. And now imagine that each of these people is an atom, okay? So all of my atoms now are going to interlock their arms. Okay, so now atoms like to move around and they like to wiggle. So all of my atoms are going to start wiggling right now. All right, but they have their arms interlocked, and so all of these atoms are pretty much stuck right in place where they are. So these atoms in this material can't move around. So what state of matter do you guys think this is? Yeah. A solid, exactly. We're a solid right now, and in solids, the atoms are really close together and they can't move around much. So now what I'm going to do to our solid is I'm going to heat them up. I'm going to put them on the stove, and so I'm going to melt them. So now instead of just interlocking arms, they have too much energy, so they can't quite do that. So maybe they're just going to hold hands, and now they have more freedom to move around. Okay, so now with this more freedom to move around, what state of matter do you guys think this is? Just shout it out. Liquid, exactly. And so now what I'm going to do is I'm going to put our liquid back on the stove, and these atoms are going to get so much energy, they're going to be jumping up and down. And they aren't even going to be able to hold on to hands. They're going to be running around like chickens with their heads cut off. All right, so what state of matter is this now? A gas, exactly. All right, let's have a round of applause for our volunteers. All right, you guys can go sit back down now. Thank you. So we saw that when we turned our liquid into a gas, all of these atoms were running around and they took up a lot more space. So that's really important. And today we're going to talk to you guys about a few different things with science, and we're going to show you some of the really cool things that you can do with our knowledge of science. And to start off, I'm going to hand the microphone off to Conan, and he's going to talk to you about something really, really cool.
All right, everyone. So we just learned about the states of matter, and I'd like to introduce this next demo to you guys by showing you guys this thing here. All right, so what I have here is a balloon, and this balloon is filled up of air. Now, can anyone tell me what state of matter air is? How about you in the front? Okay, any ideas? Okay, maybe not. What about you? A gas, exactly. So that's exactly what state of matter this balloon has inside of it. It's just air, and air is a gas. Now, there's something very interesting about air. Air is actually made up of mostly of this stuff called nitrogen. And nitrogen is actually what makes up 78% of the air around us. And it's actually not oxygen. So what I have in these space-looking like glasses things are just basically some nitrogen, but it's liquefied. So I'm going to pour some out here to show you guys. And this nitrogen is really, really, really cold. In fact, it's minus 320 degrees Fahrenheit cold. And so that's colder than both poles of the Earth. It's colder than anywhere on Earth. So when I poured this out and it hit the table, it started just boiling away. Now, inside of this balloon, this is mostly just nitrogen. And what I have in here is basically just the same stuff, but really, really cold, so it's in its liquid form. So what do you guys think will happen when I put the balloon inside of the dewar? Let's have someone on this side. What about you? Yep, you. Yes. It might pop. Okay, that's a good idea. Let's have one more idea. What about you? It's gonna freeze. That's a good idea. So, Scott has an idea. What do you think will happen?
I think it'll catch on fire.
You think it'll catch on fire? That's a good idea. It's steaming, right? Maybe it's really, really weird and something crazy will happen. Well, we're scientists, right? So we like to do experiments. I think what's going to happen is that since most of the liquid nitrogen in here is so cold that it'll just, take the gas inside and make it really, really cold, and then it'll turn into a liquid. So we're scientists, and we'll do an experiment and see what happens. Oh, wow.
Whoa, Conan, where'd all the air go? Did you pop a hole in that?
I actually didn't. So what's happening right now is that it's exactly what I said. The air inside is turning from a gas to a liquid, and so it's taking up a lot less space. And as it's taking up a lot less space, it's beginning to shrink. All right? And I can prove that I didn't pop a hole in it so that all the air went out. The air is all still in there. And I can prove this to you because if I take it back out of the liquid nitrogen, and if I just let it expand again, all of the air fills up the balloon again. And what's happening now is that the liquid that was inside of the balloon is turning back into its gaseous state, because since it's so hot compared to the liquid nitrogen that's inside this balloon, it'll just boil away and it'll turn back into its gaseous form and fill up this balloon. So I've got some more cool demos with liquid nitrogen, and my friend Taylor here is going to help me with some of these demos.
Hi guys. All right, I'm going to talk to you a little bit more about liquid nitrogen. We just saw with Conan what happens with liquid nitrogen when you take a gas and turn it into a liquid, and now I'm going to take a liquid and turn it into a gas. So, do you guys know what this is? No? What does it look like that maybe you've seen before? You can shout it out. A cannon, right? So this is our little physics cannon. It's small, but it's pretty heavy, and it still does some cool stuff. So I'm going to use my liquid nitrogen that Conan was just using for our cannon. As you saw, liquid nitrogen is really, really cold as a liquid. And our cannon here is room temperature, which is really, really warm compared to our liquid nitrogen. So if I pour the liquid nitrogen into our cannon, it's going to heat it up and turn it into a gas, which means it expands. It's going to take up even more space. So I have corks right here, which we're going to try to maybe launch. If I put the liquid nitrogen in here and it turns into a gas, and then I put this cork on here and close it off so the gas can't go anywhere, what do you think is going to happen to this? Right here. Just fall off? Let's see. Think it's going to fly off? All right, well, we're going to try this out. My friend Katrina's going to go over here, and I'm going to pour this in here. And when I pour the liquid in, it's going to start to heat up. You can hear that right now, and that's the gas trying to escape through this little hole right here because it has nowhere else to go. All right, I'm going to do that one more time for you guys. All right, I'm going to pass it off to my friend Scott. He's going to talk to you a little bit more about liquid nitrogen.
All right, I've got a little story to tell you guys. So here at the physics van, like I said before, we have all this stuff. We pack it up in our van and go traveling around to schools just like yours. But we actually live inside our van. And you know, there's not a whole lot of space inside our van, and it gets kind of cramped sometimes. You know, especially when it's like 12 o'clock at night and I want to listen to some music, but Conan wants to get his beauty sleep, so he doesn't want me to listen to our music. And so we kind of get on each other's nerves because we're all cramped into the van. So I had a really great idea. I would build us a house so we have space to live outside of our van and we wouldn't get on each other's nerves as much. So I got a piece of wood and I got a nail and I'm ready to build our house. All right, let's get this started. Ooh, hammer. Hey, guys, where's the hammer?
Conan, I thought you were bringing it.
Yeah, Conan, did you pack the hammer?
I thought Lauren was packing it.
Oh no.
That was bringing it.
Uh-oh. Well, I guess we forgot our hammer. Gee, do any of you guys have a hammer? No. No? Yes? Do you have a hammer? Oh, but it's all the way at home. Okay, well that's too far away. Well, we kind of need a hammer to build us a house. Gee, what could we use as a hammer right now? Oh, hey, Katrina, what's that?
Oh, this is my breakfast. It's a banana.
Oh yeah, that kind of looks like a hammer.
This?
Yeah. Do you think I could borrow that and use it as a hammer?
But I'm really hungry.
But you're hungry? Okay, I'll give it back, I promise. It's for science.
Okay, if it's for science, just
All right.
let me try to get it back.
Okay, so here we have Katrina's banana. It kind of looks like a hammer. Do you guys think this will work? No? Okay, well we're scientists here and we like to run experiments and see how things work. So let's just give this a try. All right, ready? Oh, well I guess that didn't work very well. Here's your banana, Katrina.
Yeah, thanks.
Oh boy, okay. So why didn't that work? Anybody have any ideas? Yeah, what do you think?
It's too soft.
It's too soft, exactly. The banana's too soft. So the banana is actually made out of mostly water. Just like you and me, the banana has mostly water inside it. And so imagine trying to hammer this nail in with a water balloon. You know, that wouldn't work very well. So what can we do to the water, which is a liquid, inside the banana to make it harder? Maybe we could use it as a hammer then. Any ideas? Yeah, what do you think? Make it into a solid, yeah. How could we make it into a solid? Yeah. What was that? We could freeze it? Yeah. Yeah, exactly. We could put it inside the liquid nitrogen and then it'd be really cold. So I think we actually have a banana in the liquid nitrogen ready to go. So Lauren's gonna get this out for me. And let's see if we can use this as a hammer. All right, so here we have our nail ready to go. There we go. It works like a great hammer. Oops, frozen banana. All right, now I'm going to hand the microphone off to David, and he's going to talk to us a little bit more about liquid nitrogen.
All right, so Scott was just showing us what happens if we take a liquid, like the water in the banana, and turn it into a solid. Now I want to talk about what happens if you take a solid and just make it colder. So does anyone know what this is? Right, I hear bouncy ball. Yeah, this is a type of bouncy ball called a racquetball. And so, does anyone know what bouncy balls are made out of? If I could get maybe one person, right here, yeah. Yeah, right, rubber. And so rubber is basically just a chain of atoms, and they're all connected together, and there's some space in between these chains. So it can kind of move around and flex. So when I take this bouncy ball and I throw it against the ground, even though it's a solid, it kind of compresses because these chains can flex a little bit, and it bounces back up to me. So what do you think would happen if I took this, though, and made it colder? Well, as we saw before, when you're, kind of have solids, there's only so much room to move around. And Scott was heating people up, and they had more room to move around, but if you make them colder, they have less. Okay, so maybe, can we get one guess on what do you think will happen if I take this and I make it colder? Yeah, right here. Right, maybe it won't bounce. That's a great idea. Can we get one more idea? Yeah, in the gray right there. It might break. Okay, well, as Conan was saying, here in science, if we don't know what's going to happen, we like to test it. So if I could have one of my friends come over. What I'm going to do is, when I'm ready, Scott is going to pull one of these racquetballs out of the liquid nitrogen that we put in earlier. And then I want you to watch closely, because I'm going to come over here and I'm going to throw it against the ground, and we'll see what happens. So, like we were saying, we have these chains of atoms, and when I make it colder, they can't move as much. So, they shatter. All right, and now I'm going to pass it off to my friend Lauren, who's going to show you some more cool science stuff.
So I'm really excited, you guys. We're like, this is my favorite demo ever. So this is my favorite because it always works. So I'm going to take this vase, and I'm going to put it down on this desk, and it's going to do something amazing. So can I get a countdown from 5? 5, 4, 3, 2, 1. Oh man, it's so cool. Isn't that great? Oh, okay, so Katrina and David missed it because they're cleaning up racquetball pieces, so we'll do it again. Make sure you watch really closely. Okay. And if any of you missed it too, just make sure you watch really well this time. Are you ready? Let's have another countdown. 5, 4, 3, 2, 1. Oh, it's so cool. Oh, man. I love it. Wasn't that great? Well, what happened? Nothing. Exactly. Nothing happened. Isn't that wonderful? No? Okay. Well, actually, it's kind of an important thing in science. See, there's this guy a long time ago. It was a really smart scientist named Isaac Newton. And what he told us was if something is at rest, it's going to stay at rest. So if this vase is just sitting here not moving, it's going to stay just sitting here not moving. And the same is true if you have something that is moving. It's going to keep on moving until I put a force on it to stop it, and it's just going to stay there and sit there and not do anything. So I guess that's sort of okay. But you see, I was at my friend's house the other day, and we were talking about science, and we had this lovely dinner set up. So I was at Katrina's house, and we had a nice dinner with our nice tablecloth, and we had a candle, super fancy dinner, and of course our vase. And so, you know, she made this stuff called lobster bisque, and I don't really know what lobster bisque is, but it looked kind of gross. So, you know, I accidentally spilt it all over the tablecloth. And you know, I felt really bad because Katrina tried really hard. It was a lovely dinner setup. And so I figured I should help her clean up. So I was taking the dishes one by one off the tablecloth, and it just took so long. So I was thinking, remember what Newton said, that if these dishes are just staying here not moving, they're going to staying there not moving. So maybe if I take the tablecloth out from underneath them.
My dishes are moving.
They're moving?
Yeah. Everything.
Did you see the dishes move? Yeah? Well, I mean, Newton couldn't have been wrong, could he? Why do you think the dishes were moving? How about way back there? What do you think? Yeah. Yeah, so the dishes are on the tablecloth, so maybe there's friction in between the dishes and the tablecloth, so the tablecloth is moving the dishes. That's a really good idea. Well, you know, I have to clean this tablecloth somehow, so maybe you think if I just pull on it really, really fast, do you think that would work? No! No? You think that would work? Okay, well, let's try it, but if it doesn't work, then the dishes will crash and we'll have fire everywhere, and that'd be cool too, right? Okay. Well, let's give this a try. Can I get a countdown from 3? 3, 2, 1. Okay. So we have a really quick disclaimer for you all. This is a very special tablecloth, and it's actually, we altered it a little bit to take out the hem on one side, so there isn't this ridge to catch on our dishes. And it's also very slippery. So please do not try this at home. We don't want you to break your dishes and get in trouble. And so just please don't do this at home. All right, thank you. I'm gonna pass this off now to my friend Katrina. She's gonna show you something really awesome.
All right, so we're going to keep talking about forces a bit. So I want everyone to do an experiment. Everyone take your hands and clap them together. Now start rubbing them together really fast. What do you guys feel? That's right, it's getting really hot because there's friction between your hands, so it's causing it to heat up. So now everyone take your hands and put a little gap of air between it. Okay, now rub it. What do you guys feel now? That's right, so when we put that little gap of air there, it reduces the friction between our hands, so we're able to move them really easily. But that's only kind of cool. And in physics band, we have the saying, if something's kind of cool, we like to make it bigger and put a person on it. So I want to show you guys our very own hoverboard. So the way it works is my friend Scott sits on the stool on top of the board, and I push on him, so then he's able to just float across the floor. You guys ready to see this? Yeah. Okay, 3, 2, 1.
That didn't work.
Okay, push harder. Okay,
Yeah,
we'll
push
try
harder.
that.
All right.
1, 2, 3. Why isn't this working? Yeah? Okay, so you guys think it's because I'm pushing on him? Well, okay, I'll try pushing on the board this time, see what happens.
All right, let's give this a shot.
Okay, ready? No, it's still not working. Whoops. Yeah, why isn't this working? The stool is too heavy. Yeah, well, so maybe like Scott's pushing down on the floor, so it's creating some friction between the hoverboard and the floor. So what's something that we could do to reduce that friction? Yeah?
Well, if he was weaker, you could push him.
Well, except he's supposed to be able to ride this. Like anyone should be able to ride this one if it works, prize. So what could we do to get rid of that friction. What did we do before? Yeah? Well, the whole point is that I should be able to let him ride. So what can we do to reduce the friction while still having Scott on there? Yeah?
Make it hover.
Make it hover. So how could we make it hover?
Get some air.
Exactly. So if we put some air under there, then it should be able to reduce the friction and we'll make it work. So I'm going to go ahead and blow some air under here and we'll be able to make him float. Okay. That should be good. We'll try it. Okay. 1, 2, 3. No, still not working. Okay, I'm hearing a lot of people say that we need more air. Okay, so David's going to help me blow and we'll be able to get this. Okay. Okay, I think that should be good. Okay. 1, 2, 3. Behind me? Hey, Taylor, Conan, what's that?
It's a back scratcher.
A back scratcher?
Yeah, back scratcher.
Well, it says weed eater on it, and it looks kind of like a leaf blower.
Are you sure?
I don't know, do you think I could borrow it? See if it works?
I guess, sure.
Thanks. All right, that looks like it'll apply a little bit more air. All right. Thanks, Scott. All right, so this hoverboard, it's really just this big block of wood with a tarp over it. And so we've got this hole on the top where the air can go in, and then it can come out on these holes on the bottom. And so we're able to get that layer of air there, get rid of the friction, and Scott can go floating across the ground. So you guys can make one of these at home if you really want to as well. And so now I'm going to pass it back to Lauren to talk to us more about forces.
All right. So remember how we were talking earlier about Isaac Newton and his laws of motion? So if something's at rest, it stays at rest. And if something's moving, it stays moving. Because when there's a force on something in one direction, it starts it to move. So another thing that Newton told us is that for every action, there's an equal and opposite reaction. So this is why I don't fall through the floor when I'm standing on it. Because even though I'm putting a force down on the floor is also pushing back up on me the same exact amount in the opposite direction. So actually, even if I get one of my physics band friends up here, we could show this in another way, where if I'm pushing on Conan's also pushing on me, so we're not going to move because we're pushing on each other in equal and opposite directions, except for when I move out of the way. Conan then falls to the ground because then there is no more force on him pushing, so he's pushing in one direction and he starts moving. So another way we could show this is with a balloon. So this is actually what we call our very highly calibrated elastic air reservoir. And I'm going to fill it up with some air. And so what I'm going to do is I'm holding on to it right now, so nothing's going to happen. But when I let go, the air is going to push out and make a force in this direction. So it's going to start moving. But which way do you think it's going to move if it's going in this direction? Right. So if the air is pushing in this direction, the balloon's going to go in this direction because it's equal and opposite. So let's try this out. Right, so it goes in that direction. So again, that was sort of cool, but maybe not that cool. And like we said earlier in Physics Fan, there's something that's kind of cool. We like to make it bigger and put a person on it. So over here, we have what we call our rocket cart, and we have our big red steel balloon on it. So this fire extinguisher, it's actually, unlike your normal fire extinguishers in your school that are full with flame retardant, we actually have CO2 gas in this, so it's just like our regular balloon. So what's going to happen here is Katrina's going to pull the trigger on the fire extinguisher, and a whole bunch of CO2 gas is going to come out and push in this direction. So which way is Katrina going to start moving? Right, she's going to go in this direction and just go off in the distance over here.
Wait, Lawrence, you don't want to hurt their nice table.
Oh, yeah, because, yeah, Newton did say that if something's moving, it's going to keep on moving. So, yeah, it's going to go and hit the table over there.
What about me? I don't want to crash.
Well, I mean, it's a really nice table, so we don't want to hurt the table. So maybe we could get one of our physics friends. And, okay, so David's going to put a force on Katrina, and then that should stop Katrina. Okay, so let's try this out. You're going to want to cover your ears because it's going to be kind of loud. But let's get a countdown from 5. Ready? 5, 4, 3, 2, 1. Okay. I'm going to pass this off to my friend David now, and he's going to talk to you about something new and exciting.
All right. So, Lauren was just talking to us about forces, but now I want to talk about air. So can someone remind me what state of matter is air? Yeah, in the black shirt right here. Yeah, you're right. Yeah. Right, air is a gas. So as Conan was saying, air is kind of made up of stuff maybe, so, you know, it has some like nitrogen in it, but it's kind of hard to see. And, you know, is it really made up of stuff? Well, if it's made up of stuff, it should weigh something, right? So if I put my hand out, it seems like if I, you know, this ball's made of stuff, and if I put my hand out and hold it up, I can feel it. But the air is made of stuff too, so why can't I feel it? Well, the air is pushing on all sides of my hand, so maybe it's just, you know, like applying a force on the bottom and applying a force on the top. But, you know, that's not really very scientific, and we can't show anything cool with that. So, back in the 1600s, this was a popular question, and a guy named Otto in a town called Magdeburg had an idea of how to solve this. So he had a ball, which is just like a metal ball, and he cut it in half, and he hollowed out the inside. And ours here has a valve on it as well. So what you can do with this is, if the valve is open, air can move from the inside out, and if I close it, then they're separate. Okay, so that's kind of interesting, but what can I do with this in order to see whether air weighs something? Well, okay, so if air does weigh something, then it's going to be kind of like bouncing around like we saw earlier, and it'll push a little bit, apply little forces on the outside of this. And when I have air on the inside and air on the outside, and they're applying little forces, those all balance out and nothing happens. Okay, but let's find out, let's think, what would happen if I took all the air from the inside and moved it out? Okay, maybe we can have a guess. Yeah, right here. Okay, maybe we can't open it. So I brought our very own vacuum pump here, which allows me to, when I connect this hose, it allows me to take all the air out from the inside. So I'm going to connect this up, and Scott's going to help me by turning it on. All right, and let's test it out. So, okay, it feels like, you know, I can't open it. So that proves it, right, guys?
How do we know you're not faking it?
Okay, I could be faking this. Maybe I could get 2 volunteers from the audience to try to help me pull this apart. Yeah, one right here and one right here in the green shirt, yeah. So if you, yeah, come on up. Yeah, come on up. So if you guys could just come up here and take this and each try to pull on this and see if it comes apart. So if air does weigh something and I took all the air out from the inside, they won't be able to pull it apart. Is it working? No. Okay, it's not working. Maybe we need some of your teachers who look a little bit stronger to come up here. If you guys could take a seat. Thank you. All right, yeah, 2 teachers. Got one here? Yeah, great. So they're looking pretty strong. So maybe we could have, if you could go ahead and pull for me. Okay. All right, not working, right? Okay, so it does seem like air weighs something, but maybe we need someone even stronger. So some of my friends here, they work out. So they could be pretty strong, and maybe they can pull this apart. Can I get 2 of my friends up here to try to pull this apart?
We got this, Conan.
Yeah. All right.
Okay, so it seems like they can't pull it apart. What happens if I open this valve here and let air back inside? Oh. Okay. Thanks. So I guess that kind of proves it, right? So when we had no air on the inside, they couldn't pull it apart. but once I let air go back inside, suddenly there's air on the inside, there's air on the outside, all the little pushes balance out and they can pull it apart. So that's kind of cool. Now I'm going to pass it off to my friend Scott, who's going to tell you some more cool stuff about air.
All right, thanks, David. That was pretty cool. So we've learned that air definitely weighs something, and it's made of stuff. And so you guys have probably been outside on a windy day, and you've felt the air, the wind, just push into you. So you can feel the air definitely weighs stuff because it pushes into you when it's a windy day outside. So there's something kind of cool about air and the way it pushes. And a guy named Bernoulli, he was a scientist a long time ago, and he said that if air is moving in one direction, say if the wind is coming at you, then it pushes harder in the direction that it's moving. But if air is moving, say this direction, it can't push as hard in the other directions. So that's kind of cool. And to demonstrate this Bernoulli's principle to you, I'm going to use some of my special science paper here. So I'm just going to get a little piece of science paper. And what I'm going to do is I'm going to blow air over the top of the science paper. And since air on the top is moving, that air can't push down on the science paper very hard. But the air beneath the science paper isn't moving, and that can push up harder than the air on the top is pushing down. And so we'll see that just by blowing air over the top of the science paper, it'll float into the air. All right, you guys ready? Yeah. Pretty cool, huh? No, it's not that cool? Okay. Huh. Oh, this is lame? Lauren thinks this is lame. What do you guys think? Lame? Oh. But I used my special science paper. I bought it online just for this.
I'm pretty sure that's just toilet paper.
It's just toilet paper? But I paid like $200 for this online. Oh. Okay, well, maybe that's not very impressive, but Bernoulli's principle is still right. So, would you guys be impressed if I could make this soccer ball float by blowing over the top of it? Okay, well, let's just give this a try. I'll just blow air over the top, and since that air is moving, it can't push down very hard, but the air beneath isn't moving, and that'll push up and keep this soccer ball in the air. All right, ready? Oh boy, that's not working. Maybe I just need a lot more air. Here, Katrina, come help me blow air. All right, ready? Oh no. Man, why isn't this working? Why isn't this working? We need more air, a lot more air? Oh yeah, we can use that back scratcher from before. That'll produce a lot of air, right? Here, Conan. Yeah, bring that up, Conan. Let's get this working. All right, so I should be able to produce enough air that I can probably make the soccer ball float. All right, let's give this a try. All right, thank you guys. Now I'm going to pass the microphone off to Lauren, and she's going to talk to you a little bit more about air.
Okay, so I'm going to start off here with a question for everyone. How many of you have ever had a birthday? Okay, so it seems like, except for some pretty young teachers in our audience, we have all had a birthday. So that means you should all be expert candle blowers, right? Okay, so I bet that if you all stay exactly where you're seated, because we're all experts at blowing out candles, if I hold this candle here and you all blow at the same time, you should be able to blow it out, right? Okay, well, go ahead and try. Well, you're too far away. Well, I guess that makes sense. See, if we put our hands in front of our faces and blow, we could feel the air really strongly, right? But if we put our hands farther away and blow, we can't feel it as strong because the air that's moving in that direction spreads out as it travels and is not concentrated to blow as hard at that one point. But you know, I'm really good at blowing out candles, so I bet you if Katrina holds this candle over here and I come all the way over here, that I could blow that candle out. You ready? But I'm going to cheat a little bit. See over here, we have our Vortex Generator 9000 Plus Millennium Edition, which is 1,000 better than the 8,000 edition. But all it is really is we have a box with a hole cut out in the front, and then a shower curtain in the back. So what happens is when I hit the shower curtain in the back, it's going to send some air moving forward. And the air that's in the middle is just going to come straight out this hole. But the air that's right next to this side here is going to experience some friction along this edge of the vortex generator. So what's going to happen is the air on the edge is going to start to move a little slower than the air that's moving out in the middle. And it's going to start curling around itself. And it's going to send a vortex of curling, swirling air in this direction. So hopefully it will be going in that direction nicely so I could hit out the candle. So let's try this, see what happens. Yeah, that's a problem because I really can't see where I'm aiming. But I think in nature, there's this concept of swirling vortex of air moving that you could actually see. Well, what do you think that is in nature? What do you think in the blue and orange? Yeah. Say it again. A hurricane. Yeah, both of those are right. So hurricanes and tornadoes, they're like swirling air, and they pick up stuff like dust and houses and cows and stuff, right? So then that's like stuff that we could see. So I need to put something in here that we could see so I could see where I'm aiming. But luckily, my friend Scott here, he's actually a DJ on the weekends. And so he lent us his fog machine. So we're gonna fill up our Vortex Generator 9000 Plus Millennium Edition with some fog, and hopefully we'll be able to see it now so I can see where I'm aiming. Okay, so we got a little fog in there now. So maybe now I could blow out that candle. I'm going to pass this off now to my friend Taylor, and she's going to talk to you about something new.
I'm going to talk to you guys a little bit about something called electricity right now. So does anyone have an idea of some things that use electricity? Let's see, right here in the pink. A light bulb, all right. Orange? What'd you say? A computer, that's a good idea. How about one more? Let's see, in the blue right here. A refrigerator? Yeah, awesome. All those things use electricity. Now, what is electricity made out of? How about in the red and white right here? Power wires, that's a good idea. How about one more? Let's see. You right here. Energy? All right. Those both really good ideas. Electricity is made out of something called moving charges, and they basically all come together and make electricity. Now, these charges are opposites, and they're positive and negative. But it doesn't really matter what we call them, so for now, we're going to call them blue and red. Now, these charges are kind of strange. When you put two similar ones together, like these two blue charges, they don't want to be anywhere near each other. They're just going to completely repel. But if I have two opposite ones, like red and blue, they're going to stick together and they want to be together. So I'm going to turn some of my Fizz Van friends into some charges, and we're going to see what happens. So we have Katrina and Conan. I'm going to turn Katrina into a blue charge and Conan into a blue charge as well. Uh-oh. Oh no, they don't like each other at all. Okay, well, in Fizz Van, we need everyone to be friends and to get along, so I'm going to fix this a little bit. I'm going to make Katrina a red charge now, so she's opposite of Conan. Wow, okay, well, now they really like each other, and I don't want them to get too dizzy, so I'm going to stop this really quick. All right, now I'm going to pass this off to my friend Katrina, and she's going to talk to you even more about electricity.
All right, so you guys have probably been wondering what this big spacey looking thing is, right? Well, this is called our Graff Generator. And what it does is it separates charges. So there's this moving belt in here, and it brings one type of charge up to the top. So we'll just go ahead and say that's a red charge. And it brings the opposite type of charge to the bottom, so we'll say it's blue. And then we've got this wand here that's connected to the bottom, so it also has a blue charge. So when I turn this on, there's going to be one type of charge collecting on this top ball and a different type of charge collecting on this small one, and these different charges are going to want to get together. So let's go ahead and see what happens. You guys see that? So what's something in nature that reminds you of? Yeah? Exactly, it's like lightning, and that's all lightning is moving charges. So when you have like one type of charge in the clouds and the opposite charge on the earth, those charges want to be near each other, so you get the lightning as all those moving charges going through. So we've got some other cool stuff we can show you with our Van de Graaff generator. So what I have here are a bunch of pie tins. Does anybody know what a pie tin is made out of? Yeah? A metal, exactly. So they're not made out of pie, and they're not made out of tin, but they're made out of a metal called aluminum. And metals are something that are called conductors, meaning that the charges can move through them really easily. So when I put these pie tins on the top here, they're going to all get the same type of charge as what's on this big ball. So what do you guys think is going to happen to the pie tins? Okay, I'm seeing like this type of motion that they'll just like go apart. All right, well, let's go ahead and do an experiment and see what happens. See, yeah, so you saw they were all getting the same type of charge, so they didn't want to be anywhere near each other. So they just all flew apart. I've got one other thing to show you guys. So my friend Scott here is going to stand on this stool. And he's going to hold this metal rod that connects him to the top of the Van de Graaff generator. So all the charges that were in here are going to go into Scott and spread out, and they're all the same type of charge. So they're going to want to try and get away from each other. So when I turn it on, it's behind you. Okay. So when I turn this on, you'll be able to see like all the charges trying to get apart. And so like they'll even go to the ends of his hair and to like fly apart.
Can you see it? I can feel my hair standing up.
Yeah, you guys see his hair standing up?
I don't see anything.
No.
Maybe my hair's too short.
Okay, well maybe if we give him this awesome wig, we'll be able to see it.
Oh, yeah, okay.
Doesn't he look beautiful?
All right.
All right. So you guys can see some of those orange pieces are sticking up now because they all have the same type of charge and are trying to get away from each other. All right. So now I'm going to pass it off to Conan for one more electricity demo.
Alrighty. So you might have seen some Van de Graaff generators and stuff, but I've got what's called on the box the decorative light of the future, and it's this thing right here. Now, this thing you might be able to see that it's got a bunch of like electricity or lines and that are like, flowing, right? Now, it's actually what's called a plasma ball, and it's actually just really, really simple. There's one type of charge on the inside of the sphere and another type of charge on the outside of the sphere. So now the same type of charges don't like to be near each other, right? So they want to get apart from each other as much as possible. So they're going from the inside sphere to the outside sphere. And since they want to go as far away from each other and they want to go into like some big stuff, right? What's something that's really, really, really big? Maybe something that's, as big as possible that you can think of that the charges can flow into. Anyone have any ideas? How about you in the white shirt? The Empire State Building, yeah. But what's that building on? What's something even bigger that building is on? Like something maybe floating in space. How about you in the blue? Yeah. Huh? Earth, exactly. So that's exactly what I'm going to do, and I'm going to let the charges flow through me into the Earth. Isn't that cool?
Whoa, Conan, how do we know that those charges are actually moving through you? That seems kind of weird.
Okay, so Scott here doesn't believe that these charges are actually moving through me. So what I have here is a light bulb. And what happens when charges, specifically electricity, moves through a light bulb? What happens to it? Yeah. It lights up, exactly. So if this light bulb lights up, would you guys believe me that charges are moving through it? All right, so let's do that. So you can see the charges are moving from the plasma ball into the light bulb, through me, into the ground, to the Earth. Now, charges are also really lazy. So if I move it my hand halfway, the light bulb only lights up halfway because the charges would rather move through this part of my hand, through me, into the Earth, as opposed to moving to the end of the light bulb and all the way back, and then going through me to the Earth. So that's pretty cool, right? Okay, so for my next part of this demonstration, I'd like to call up 2 volunteers. What about you two in front? All right, so if I could have you two stand up on these stools right here. Okay, and face the audience, good. Now, if you could just hold hands for me, and if you could touch the plasma ball right there, put your whole palm on it, good. All right, so what do you guys think will happen if the charges are moving through her right now, okay? And these things here, these plastic stools are actually what's called an insulator, and charges don't like moving through them. So what's going to happen now is that if you could hold on to this light bulb for me, if you could hold on to this light bulb for me, thank you. So it's actually easier for the charges to move through one person, 2 people, through the light bulb, and me to the Earth than it is to move through the stools. Thank you very much, and if I could have a round of applause for our volunteers. All right, thank you very much. Now I'm gonna hand it off to Scott for some final notes.
So that's the end of our regular demos. We've got a couple more to show you, and they're gonna be nice and big demos that you really wanna see, and it's gonna take us just a couple minutes to get those set up. And so in the meantime, I'd like to take any questions that you guys might have about the show that we've just shown you or about science in general. So does anybody have any questions? I can take a few questions. Yeah.
How long have you been doing this, and how much does a plasma ball cost?
Okay, so the question is, how long have I been doing this, and how much does the plasma ball cost? Well, the plasma ball isn't that expensive. You can actually get them at most, probably at the mall. If you go to a cool store, they should probably have a plasma ball, and it's not too much, probably about $50 or so. So you could probably buy those if you want to. And I've actually been, I've been in the physics fan for 3 years now, but I've been doing science for a lot longer. So it actually started when I was in elementary school. You know, I was doing science in my science class, and I just kept with it, and I kept going until I got to college, and then I pursued science more. And now, when I'm older and still doing science, I get to play with all these cool toys. All right, how about a few more questions? Yeah, in the red. Yep.
Are you ever going to want to be a scientist?
Am I ever going to want to be a scientist? Yes, and actually I am a scientist already. So I'm a physics major at the University of Illinois, and I study physics a lot. And when I graduate from college, I want to keep studying physics because physics is a lot of fun. All right, so how about a few more questions? Yes, in the front. When did I start to be a scientist? Okay, well, if you remember at the beginning of the show, I told you that anybody who wonders why something happens is a scientist. And Albert Einstein said that. So I began wondering, why things happen, or where my mom is, when I was very, very young. So I was probably a scientist before I can even remember being a scientist. All right, how about a couple more questions? Who has some good questions? Yeah, and the orange. what kind of scientist am I going to be? So actually my interests lie in computational physics, and that just means I use computers to simulate really cool physical systems. So like say we could simulate black holes and we could simulate like galactic gas spinning around those black holes. That's actually what I research right now. And so in science you can study just about anything that you want to. There's a lot of really interesting things to do. All right, how about one more question? Who has a good question? In the back, in the green and black.
Is there any link between what we thought as magic and science?
Yeah, okay, that's actually a really good question. A lot of things that we see in nature seem like magic, like lightning. A lot of people thought that lightning was just magic before they understood that lightning was just electricity, or just charges moving from the clouds, which had one type of charge, into the ground that had another type of charge. So whenever you see something that you don't understand, you shouldn't think that it's magic. You should think, gee, I don't understand that. What can we do? Or how can I learn how that worked? And how can I better understand how the world works? Because almost everything around us, there is a real explanation for it. Like you saw that I made the soccer ball levitate, and that seemed like magic, but really it was just me applying one of the principles of science that I've learned while I was studying science. All right, so that's all the time we have to answer questions. If you guys have any more questions, you can go to, or you can do a Google search for the physics van, and you'll be led to our website, van.physics.illinois.edu. And on there, we have a feature called Ask the Van, and you can ask us any type of question about science, and one of us or one of our friends will get back to you with an answer. All right, so without further ado, we have a couple more really cool things to show you what we can do with science. And now I'm going to hand it off to Katrina. She's going to show you something really explosive.
All right, everybody. So for our last couple of demos, we're going to bring back the liquid nitrogen that we had at the beginning of the show. So what I have here is just an ordinary pop bottle. And I'm going to pour some liquid nitrogen into it and put the cap back onto it. So remember what happened earlier in the show when the liquid nitrogen, which is really, really cold, met the air that's really hot compared to it. So what do you guys think will happen when I pour liquid nitrogen into here? Yeah?
The cap will blow off.
The cap will blow off? All right, so we all remember what happened when the gas heated up, when the liquid heated up and became a gas and blew off the cork from our cannon. So let's go ahead and give this a try. All right, everyone should cover their ears because this might be loud. Oh. Well, that was fast. All right, so that gas really didn't want to be anywhere near the rest of the pop, needed way more space than what's in the pop bottle. So here's what's left of our pop bottle. See, you can see it just completely broke apart. In the van, in the van. All right, so now we're going to hand it off to Scott for one more demo.
All right, guys, I've got one final demo to show you, and I promise that everybody will be able to see it. So what I have here is a bucket of warm water, and what I'm going to do is pour a little bit of soap into this warm water here. So I'm going to have some soapy water. God, that's I guess, yeah, okay. Maybe I put a little too much soap in here. Okay, so what I have here is a bucket of soapy water. And so what I'm going to do in a second is I'm going to take this big dewar that's filled with liquid nitrogen, and I'm going to pour all of this really freezing cold liquid nitrogen into the warm soapy water. So then all this liquid nitrogen is going to heat up and it's going to turn into a gas. And if you remember from before, gases take up a lot more space than liquids do. So right now this liquid takes up just as much space as this container here, but after it turns into a gas, it's going to take up a lot more space, right? Okay, so I'm just going to pour all of this into here, and then we're going to have a bunch of gas and a bunch of soap. So what do we have with gas and soap? Any ideas? Bubbles. Yeah, I think I heard somebody say bubbles. So we should get a whole bunch of bubbles. All right. Oh, gee, I did put a lot of soap in there. Yeah, okay. All right, well, I want this to be a good explosion, so it's probably good that we used a lot of soap. All right, so could I get a countdown from 5? 5, 4, 3, 2, 1. Oh boy. Gee. I guess I did use too much soap in there. All right. All right, thank you guys. That's everything that we have to show you about science. I'd like to thank you guys for being such a great audience. And please remember all of the cool things that we can do with science. Thank you.